So this is the review for AP Physics 1, Chapter 2 and 3. We're looking at kinematics and motion in 1 and 2 dimensions. So this is a chart I put together to kind of help you with all the vocabulary and concepts of everything that we've been looking at. So you need to understand the difference between distance, displacement, instantaneous speed, velocity, acceleration, and average speed. So there's different letters, right? I mean, that's simple enough. You know, distance is d and displacement is x. Technically, right, displacement is delta x, right? It's the change in position because x is technically position. Instantaneous speed is v or u. Velocity is always v, acceleration is a, and average speed is u or v. So you have to remember which ones are vectors and which ones are not. So my vectors, let's put a v over each of the vectors. So the distance is a scalar. We can do that. Displacement is a vector. Instantaneous speed is a vector. Velocity, well, if it's velocity. If it's speed, it would be a scalar. So it depends on if it says speed. But if it does say speed, then technically it would be a scalar. Acceleration is a vector, and average speed is a scalar. So always read the question to see what they're really asking for. The equations for velocity and speed many times are the same if you're going in the same direction, but you still have to figure out which one it is. So the concept for distance is the total distance you walk. So if you look at the equation down here, it says d plus d plus d. I know this seems sort of silly, but you just add up all your distances. But let's say I'm going around in a circle. So I can't put the drawings. You're supposed to put the drawings there, but I don't have space on mine. So let's say I'm going in a circle, right? So if I'm going in a circle and I want to know the distance, and I walked from this point to this point, right, from point A to point B, then my distance would be from A to D, right? And I know that the circumference is 2 pi r, so I know my D would be equal to 2 pi r divided by 4, right? Because that's 1/4 of it. But if I wanted to know the displacement, it would be this little part, right? And we know that this is r and this is r, so my displacement, delta x, would be the hypotenuse right here. So that would be r square root of 2 if you know your triangles, or you could do the square root of r squared plus r squared, but it's the same thing, right? So the difference between distance and displacement. Displacement, it says here, difference between starting and ending position, right? So it's just the difference between the two. That's why we have that delta up there. V or U, if they use just the letter V or U with no line over it, then that's at that moment in time. Normally we put a VF or a V naught on it. And so you usually have to use a UAM equation. There's not really a drawing to go with that one. I just had a space for everything to have a drawing. But it's more just the concept that is at that instant, right? So read the question and read. It says, after 2 seconds, that's instantaneous. If it says, during 2 seconds, it moved this distance, it might be asking average speed. So you need to pay attention. Is it instantaneous or average? Velocity, direction matters. So if you go in one, if I'm looking at my velocity, if I drew a picture for my velocity, it's always going to point in one direction, right? Velocity can't have multiple directions. If I change directions, right? If I go like this is a different velocity. So this would be V1 and this would be V2, and they are not, even if they're the same length, V1 cannot equal V2 if it's not going in the same direction. If it was speed, right, if it was a U and a speed, then they could be, you know, if they're the same size and same everything, they could be, but because direction doesn't matter when you're dealing with speed. For acceleration, acceleration is the change in velocity. So A does not equal V over T. Don't do that. A is equal to delta, that is the definition, delta V over T. It's the change in velocity per time. So a lot of people are still doing this. They're still doing A equals V over T, and just don't do it, don't do it, don't do it, don't do it. If V is equal to 0, then yes, it's equal to VF over T, but only if you start at rest. Again, I don't really have a picture for that one. An average speed. So what's the difference, though, if we wanted to do average speed, maybe we can do a picture for that with goes with the velocity. So if I looked at my V1 and my V2 and I wanted to find my average velocity, this would add up, and then I would divide that value by 2, right? And that would give me V average. But if I'm trying to find my average speed, if we want to use the letter U with a line over it, right? Line, there's supposed to be a line over it, right? If I did the same thing here, you would then not do it as a vector, right? You would now add it up. If I'm doing speed, it would just be V1 plus V2 divided by 2, as opposed to using the vectors and adding them up. So it's not the same thing. A lot of people say, oh, average speed, average velocity, they're exactly the same. They're only the same if you keep going the same direction. So the equations, right, you need UAMs if you have acceleration, right, and you're trying to find displacement. You could maybe find displacement here if you didn't have acceleration. Remember, technically that's delta x, but this equation only works if it's average velocity, not for final velocity. That's why instantaneous has to be a UAM equation. And then this is average speed, so it's u, and that's just the distance that you went. So if we go back over to this picture, right, and I was trying to find the average speed, I would take, right, average speed would be equal to d over t, right, this d. But if I wanted to find the average speed, it would be, oh, I just did it backwards. Don't do it backwards. So average velocity, right, average velocity would be this one, right, which would be my delta x, this guy, right, delta x over t. If I was trying to find my average speed, then I use distance, and I would do distance over t, and I would use this one. So you're not going to get the same value, because I'm not going in one direction. Now, if I kept going this way, right, if I did that the whole time, that's a straight line, really it is, then u is going to be the same as v, because delta x is going to be this over t, is going to be the same as d over t. So as long as you go in the same direction, it doesn't matter. But as soon as you turn, as soon as you go in a circle, as soon as you change directions, then you have to separate out your velocity and your speed. Hopefully that helps. I think that's, just making sure you read the question carefully and what is it asking for. Then we talked about free fall and projectiles, right? So when you're in free fall, we remember that I know WebAssign likes negative 9.8. But I am perfectly fine with using negative 10 meters per second squared, since it's all about the concepts and I really don't care about the math, right? At the top, if it's in free fall, that means it's 0. Remember, in free fall, it's always got to be negative 10 because there can't be any air, there can't be any other forces. When you look at VF, it's equal to the negative, so one's got to be negative of the other one, right? So it goes up, right? So in one case, it's going up, and the other case, it's coming down. So therefore, they're going to be the negative of each other's when they get back to the same point. Then the time up is going to equal the time down. So concepts to remember, if I start at the bottom at, let's say, 50 meters per second going up, then I know at the top I'm going 0 meters per second, and I know that it took it 5 seconds to go up. How do I know that? Because it lost 10 meters per second every second, so that's 5 tens. When it comes down, it's going to take 5 seconds again, but now it's going to be going negative 50 meters per second when it comes down. Right? And again, it's because it takes the same amount of time. So things to remember as you're trying to do calculations, you can always use concepts. I so much prefer concepts. That means you've really got it. If you can do the math, good. But if you can do it with concepts, even better. If we're dealing with projectiles, you have to remember that it's always moving in the v direction, right? So in this case at the top, now it has a vx. My acceleration is still negative 10. Right? Because it's only if I just want to draw my acceleration vectors, here's my acceleration vectors, right? So that's my A, that's my A, that's my A. My V, though, stays the same, but I have a VY, right? Which starts off big and then goes away and then ends up going like this. Notice the direction of things, right? So here my A and my VX are perpendicular to each other, right? If we're at some angle up here, then my acceleration still points down, my VX still points sideways, and my Y still points like this, but now my velocity itself, the total velocity is pointing this way, right? So my velocity is not perpendicular to my acceleration as I go up and down. But just like free fall, it's the same amount of time up as it is down. So if I get, I know now it's getting really messy, isn't it? But if I go from here to there, right, if I'm going just to this top point, and that takes some amount of time t to come back down, it's going to take the same amount of time t, just like we did before, where the time was 5 and the time was 5, so it could be the same thing. I know that let's put it up here, that VFY at the top is 0. Right, even though it has Vx, just like before. I know that this V naught y and this VFY are the negative of each other, just like before. So if I throw it, so let's say I threw it, let's make it a 3, 4, 5 triangle to make my math really easy. So let's say I throw it at 50. So that means that it's going, let's say, 40 meters per second this way, and 30 meters per second this way, and 50 meters per second this way. Then at the top, I know V is 40, right? Because the only velocity it has is this. I know that it's going to take 3 seconds to go up, and I know it's going to take 3 seconds to go down because it's traveling at 30 meters per second, and it still loses 10 meters per second. So it's going to take it 3 seconds up, 3 seconds down. What else could I say about it? I could say that VF is going to be equal to 50 meters per second, but it's the opposite direction, right? It's going to be pointing this way when the first one was pointing up that way. Everything else is the same, and you can calculate things after that. We'll go through the math part, but that's the concepts, right? So think about it when you're doing it, right? You know how to calculate these too. If we didn't do a nice 3, 4, 5 triangle, you know that Vx is going to be V cosine theta, and you know Vy is going to be V sine theta. And then you can still do everything else the same. I just wanted to do it with some easy math. Okay? So free fall, projectiles. A is always 10. Always, always, always. Negative 10, down. One thing. It's only negative 10 if you're on the Earth. If we go to another planet, no longer negative 10. Oh, wait. Which is what it says here. Read carefully. Where do you start? Where do you end? Is A equal to negative 10 meters per second squared? You don't know that. You have to find. You can't just assume it. So let's say I throw a ball up, and it comes up to the top, and we throw it at some speed, but we have no idea what we threw it at. And maybe it says after 3 seconds, it's moving at 10 meters per second, right? If we're on Earth, if we're on Earth, then you could rationalize that, 3 seconds, 20, 30, I must have, 20, 30, 40, right? It must have been going 40 meters per second when I started, because I can count by tens, because it loses 10 meters per second every second. So we'll go 40, 30, 20, right, for every second. So 1 second, 2 seconds, 3 seconds, right? So that means that it would have been thrown at 40 meters per second. But let's say, on the other hand, I'm not on Earth. Let's say, you're not on Earth. And it says something like, okay, after 3 seconds, it's going 10 meters per second, just for the sake of argument. But let's say now it says you threw it up at, I don't know, you have to throw up something faster. So let's say you threw it up at 60 meters per second. And now I want to know what G is on this planet, because it's definitely not 10 anymore. So you go, well, you could do it with an equation. You could say A is equal to delta V over T. And you could say, okay, so that'd be 50 divided by, what did we say, 3 seconds? I don't know what that comes out to be. But you could do 50 divided by 3. You could also use logic and just say, it lost 50 meters per second in 3 seconds. You get the same thing, right? 50 meters per second in 3 seconds. Same thing, right? So read the question and see what it's saying, right? It might say between 3 seconds and 4 seconds, right? And then you know the change in time was 1 second. Anyways, read it as you go and make sure it makes sense for whatever you're doing. Okay, equations, because you guys love the math, right? The thing to remember, and I say this, and I say this, and I say this, and I know it's hard to understand, but there is no acceleration for projectiles in the x direction. The only equation you have in the x direction is this one. We can use that if a car is moving like this at a constant velocity, right? Right? I think you all got that, right? You know that V, this is technically average, is equal to x over t, and technically delta x over t. And it doesn't matter if I throw it like that or if it moves like that, it still has a constant velocity in that direction. So that's the equation I use. I can still use it here if I am doing v naught plus vf times t, but this is average v, that assumes there's acceleration, because think about it, it's really silly. If I make these the same, so v naught and vf are the same, then you just get v, and then it becomes this v, and then it just becomes the same equation you have up here if there's no acceleration. But if there is acceleration, you can use that equation. Now, these three equations are on the equation sheet. They're the only ones on the equation sheet. And yes, people have been asking me, yes, you get to use your equation sheet. So notice I did this all in the x direction, right? I put my x naught over here. Just make sure it makes sense. So it's 1/2 at squared plus v naught t. So if we go in the y direction, right? Okay, let's make another car. So my car is moving, but now instead of constant v, it has constant a, right? Which is fine. But that means that where before I used this equation because it's going at constant v, now that it's going at constant a, I'm going to use this one. Or I could use this one. Or I could use this one. And if I'm dealing with my projectile, then I would, anything in the y direction, I would use these green equations, right? So I can figure out y equals 1/2 gt squared. If I'm moving horizontally, a doesn't have to be g, right? But here, a has to be g, has to be negative 10 meters per second squared. And so any of these equations will work. Remember, if you don't have VF, use this one. If you don't have X, use this one. If you don't have T, use this one. But those equations are given to you. You should have practiced with those. Hopefully, you're feeling fairly comfortable. Graphs. So yes, there'll be graphs. We practice with graphs. So if I'm looking at an x versus t graph, then I know the slope is velocity, and technically it's instantaneous velocity, but if the slope stays the same, it's also my average velocity. A v versus t graph, the slope is acceleration. The area is displacement. So remember, we talked about how to find area. And for a versus t, the area is the final velocity. So if I show you an xt graph, and the xt graph is going like that, you know that is constant velocity because the slope's not changing. You could find your slope, which you could do delta x over delta t, right? So my slope is delta x over delta t, which is equal to v, which in this case is v average, but it's also v naught, which is also vf because it's at constant velocity because it didn't change. If I had a graph and it was xt and it went like this, then I know that my slope is increasing, so my velocity is increasing, so I have acceleration is equal to something. I'd have to have the equation to figure out what it was, but at least you can see that the slope is increasing, right? It's getting steeper and steeper and steeper and steeper, so it's going faster and faster. If it is concave downwards like this, it's still getting steeper, right? And steeper and steeper and steeper. It's just negative acceleration in that case because it's accelerating in the negative direction. If its slope is getting smaller like this, right? So here's my slope and it's getting steep, less steep, less steep. In that direction, that'd be negative acceleration, right? Because it's slowing down. It doesn't have to slow down, right? Because we're going to be in a different quadrant. Don't get really held up on it. Just think slope, right? When we're doing a VT graph, right? When we're doing a VT graph, I think you're fine for, like this would be constant V because there's no slope, right? My slope equals 0. And if it goes like this would be constant acceleration. The slope would equal something. You'd find the rise over the run. But it's the area, right? So when you're finding area, it's always bounded by the x-axis. So you could find the area there, and that area would equal my displacement from wherever I started. Remember, you got to add it to wherever you started because it's your displacement from that point in time. If it goes below the axis, which we've seen before in some of our graphs, so if we have a graph that goes like that and it's VT, like so, you find this area and then you find this area and you make this one positive and this one negative, and then you can again find your total displacement, add it to what your initial position was. And then A versus T is the simplest one in some senses, right? Because A versus T can only be straight like that, right? And if you find the area under here, that's going to be equal to the VF, right? So you can find, this would have no VF, right? The VF would be the same as V naught. So you add it to it, right? So you take the area and you add it to what the V naught was. Here you subtract it from what the V naught was. Again, use your concepts as you do it. That's it.